Hello! In this video, we are going to be talking about eigenvectors and eigenvalues for matrices. All right, and let's talk a little bit about why we like these and why we need them. Okay, so linear transformations can be kind of hard to visualize. All right, so let's say, right, we have a transformation T that's given by, right, what a linear transformation does, or one way we can view it is you put in a vector, and what the function does is it multiplies by a matrix A. And let's say that matrix is, like a 6 by 6. Okay, so that means that what we have is a function where the inputs are from R6 and the outputs are also in R6. So that's like 12 dimensions total that we would have to visualize, right? When we think about just a regular function like f of x equals x squared, we can visualize that, real number x values, real number y values. As a plane, we can even visualize, functions in 3 dimensions. But higher dimensions, we aren't that fancy. We can't really visualize that. So what eigenvectors and eigenvalues do is help us visualize how the transformation acts on certain spaces. In the spaces that we are interested in, the functions that we are interested in the vectors that we're interested in is ones where when we multiply A by that vector, we get back something really similar to that vector. So all A does to a certain vector is make it a scalar multiple of itself. So this is our main property here that we're concerned about. Okay, so one thing to note, if A is our function here, if x is our vector, right, and let's say that that vector is in Rn, that's our kind of input, and let's say that our output vector, right, it's some scalar multiple of x is also in Rn, then input is Rn, output is Rn, so that means that A has to be n by n. So these are really only for square matrices. Okay, so an eigenvector of an n by n matrix A is a non-zero vector x such that we want this property that we're talking about. A times x is equal to lambda x, where lambda is a scalar in R. Okay, so x is the eigenvector, okay, right? X is our eigenvector, and lambda is what we call the eigenvalue. Okay, lambda is the eigenvalue corresponding to x. All right. And let's write down that's good. Okay. So let's go ahead and do an example here. We have a specific 3 by 3 matrix and a vector, and we want to show or answer the question, is U an eigenvector of A? If so, we want to find its eigenvalue. Okay, so let's go back up and just remember, right, it's an eigenvector if A times x is just a scalar multiple of x. So that's all we want to do is look at A times x. All right, 3, 7, 9, -4, -5, 1, 2, 4, 4, and we're going to multiply here. And remember, with matrix multiplication, we're going to go across here and down here. Okay, so 3 times 4 is 12, 7 and -3, it's -21, 9 times 1 is 9, and then we move down a row, -4 times 4 It's negative 16. Negative 5 times negative 3 is positive 15. 1 and 1 is 1. And the last row, 2 times 4 is 8. 4 times negative 3 is a negative 12. 4 times 1 is 4. And we add all of those together. So let's see, 9 and 12 is 21 minus 21 is 0. 15 and 1 is 16, and negative 16 is 0. 8 and 4 is 12, and negative 12 is 0. Okay, so we got 0 out of this, and what we're wondering is, can we write this as a scalar times our original vector? Can we fill this blank in with a real number? And if we were in class, I would ask you, what scalar would make this true? Is there one? And you would say, yes, it's a 0. Okay, so our answer here is yes, U is an eigenvector of A, and its associated eigenvalue is lambda equals 0. So yes, because what we got here as our product is a scalar multiple of our original vector, and lambda equals 0 is the scalar, so that is the eigenvalue. Okay, so one thing to note here, all right, is that 0 can be an eigenvalue. Okay, what we talked about earlier when we said that something was non-zero is the original vector has to not be 0 to be an eigenvector, but its eigenvalue can be 0. All right, let's do one more example like this. Okay, so this time we have a 2 by 2 matrix and 2 different vectors. We want to know if they are eigenvectors. If so, find their associated eigenvalues. And we're going to do the same thing that we just did. All right, we want to check A times X for both of these. And I think it is probably a good idea for you to pause and try to just go ahead and work this and see if you get the same thing that I do. So if you're pausing, pause. And I'm going to go ahead and work it out. So here we go across and down. 5 times 4 is 20, plus 0 times 2 is 0. 2 times 4 is 8. And 1 times 2 is 2. Okay, so there we get 20 and 10. Okay, and I'm just going to go ahead and multiply the other one out. 5 times 3 is 15, and a 0 times 0 is 0. 2 times 3 is 6. 1 times 0 is 0. So what we get here is 15, 6. And now we want to think about, are these eigenvalues? So can I take this one and write it as, can I write that as a scalar times the original vector that we started with, 4 times 2? All right, and we just need to think about, okay, how would I get from 4 to 20? Well, I would multiply that by 5. And then does that work for the other one? Well, 5 times 2, that does give me 10. So the answer for this one is a yes, and the corresponding eigenvalue is 5. And over here, we want to look at the same thing. Can we write it as, what was our original vector? 3, 0. Can we fill in this so that when we scale, we get what we ended up with here? So what would we need to multiply by that 3 to get 15? We'd need to multiply by 5. So 5 times 3 is 15, and then we see if that works for the bottom one. 5 times 0 is 0, so this doesn't work. So the answer for this one is no, and that is because A times 3, 0 does not equal lambda times 3, 0 for any lambda that we choose. All right, we'll go ahead and stop there. We'll be back in the next video with more on eigenvalues.